All right, we will get started for today. Should be a relatively quick class. Don't have that much to cover and really no math involved for today. So those of you who don't like math, rejoice. This is all about trends in the periodic table today. So let me get the PowerPoint up. All right. Happy Friday the 13th, everybody. Spooky, spooky. So what we're going to talk about first off is electron affinity. Now, on Wednesday, what we talked about was ionization energy, right? And ionization energy, there we go. There's my, whoa, pen's a little bit off today. So ionization energy is the opposite of electron affinity. G, there we go. Ionization energy is how much energy does it take to remove an electron, right? And all of those energies were positive because it takes energy to remove an electron. What we're going to talk about here is electron affinity. That is, when an element gains an electron, how much energy do they put out into the universe? So electron affinity is usually always exothermic. That is, it's usually always negative. And we have some trends for electron affinity. And these trends aren't nice and neat, but there are some trends in the periodic table. First, with our alkali metals, let me get my spotlight here. So our first trend is with our alkali metals. And as we go down the column, our numbers become more positive. So we start here at hydrogen minus 73, all the way down to rubidium at minus 47. Note, not every group does this, right? So like if we go to the halogens, we actually go up once when we go to chlorine. Same thing with sulfur. But if we're looking at group 1 metals, as we go down the periodic table, our electron affinities become more positive. And remember, when we're talking about energy, negative energy is generally good. If you are releasing energy in the world, that means you're becoming more stable. Now, as we go across a period, that is, we're going from left to right, generally we become more negative. So if we look in our P block here, if we're going from boron to fluorine, generally we become more negative. But there is a big exception, and that's in group 5A. So where nitrogen, phosphorus is. These elements don't want to get an electron as much. Basically, the reason why that is, if we were to draw our electron orbital diagram, where's my pen? So here we are in the P block. And so for nitrogen, we have 3 electrons in our P orbital. If we were to gain another electron, the only place to put it would be to pair it up with another electron. Nitrogen does not want to do that. We'd rather keep our electrons separate if we can. So nitrogen really does not want to gain another electron. It is unfavorable for nitrogen to be negative. And in the vast majority of reactions we see in chemistry, nitrogen's always positive. It wants to lose electrons. Phosphorus, As and Sb, follow that trend somewhat, but it's not as pronounced as nitrogen. But generally, moving from left to right, we become more negative. Group 2A does not want to get an electron for this for a very similar reason. In group 2A, we have a full s orbital. We have 2 electrons in our s orbital. So if we were to put another electron in, we'd have to create a whole new orbital, which doesn't want to happen. And the elements that are the most negative will be our halogens. So halogens have the most negative electron affinity. Remember, electron affinity is wanting to get an electron. And the reason they have the most negative is that they are 1 electron away from having a full octet. That is, they are 1 electron away from having the electron configuration of our halogens. So they really, 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 really want to get that 1 electron. So what I want us to do is look at the trends on our previous page and see if you can tell me from each of these pairs which element is going to have a more negative electron affinity. Now I have a poll for this, so see if you can use the ideas we just talked about and see which ones have the more negative electron affinity. So do about 30 more seconds. EA is just the opposite of IE. Yes, electron affinity and ionization energy are the exact opposite concepts in that electron affinity is gaining an electron, ionization energy is losing an electron. And they are kind of opposite. So if, for example, the halogens have a very negative electron affinity because they really want one more electron. They have a very positive ionization energy because they don't want to lose electrons. So it's not as simple as being complete opposites when we talk about energies, because there are, once you get into a lot of different elements, each element might have like an exception here or there. But in general, generally speaking, if something wants to gain an electron, they don't want to lose those electrons then. So yes, if you have a very favorable electron affinity, you're going to have an unfavorable ionization energy in general. All right, let's take a look at this. So first one, sodium or rubidium. So sodium is higher in the periodic table in the same column as rubidium. So for A, that is sodium. So sodium is the answer for A. Boron or sulfur. Here, sulfur is has more electron affinity. And let me actually go back to the periodic table so we can be looking at that. So we were comparing boron and sulfur. So boron's right here, sulfur's here. So we are further to the right, and that's going to play a big role in electron affinity. The closer you get to your halogens, the more your electron affinity will become negative. Carbon and nitrogen. All right, we had a 50-50 split here. All right, so this is something you just kind of have to memorize, right? Nitrogen does not want to gain electrons, and it's for the reason I stated when I was going over that. Nitrogen has 3 electrons in the p orbital already. To gain another electron, it would have to pair up its electrons in the p orbital. You might want to write that down if you have trouble remembering that, right? Nitrogen has 3 electrons in the p orbital. To gain another electron, you would have to pair them up. Nitrogen does not want to do that. So carbon has the most negative electron affinity. Fluorine versus lithium. Fluorine is the correct answer there. Fluorine is a halogen. Halogens love electrons. Magnesium versus sulfur. Magnesium, any group 2 metal, does not want to gain electrons. Metals in general want to lose electrons, but they really do not want to gain an electron because they already have a full s orbital, right? To gain another electron, you have to put it in the p orbital. So if you're comparing magnesium with sulfur, sulfur is going to be the answer. So it should have been sodium, sulfur, carbon, fluorine, sulfur. Any questions about our electron affinity? All right. The next thing we're going to look at, our next trend, is metallic characteristics. And we actually already talked about this somewhat at the very beginning of our course, where we looked at the types of elements, and we said there's 3 types, right? We said there's metals, we said there's metalloids, and there's non-metals. And our trend, if we're just looking at what is more metallic, basically, the bottom left is the most metallic, and the top right is the least metallic. And you should already kind of know this based on what we talked about at the beginning of the semester, where we said on the left side, you're more metallic, and on the right side, you're a non-metal. Well, let's actually put that to a trend now. As you move right to left, you become more metallic. As you move down, you become more metallic. Our exception to that is hydrogen here. Hydrogen is not a metal. Even though it appears in group 1, hydrogen is our exception to that, in that if you were comparing hydrogen to something else, hydrogen's not a metal, it's a gas. Well, let me say that again. Hydrogen's not a metal, it's a non-metal. But as you move to the bottom left, you will become more metallic. So another simple question here. What is more metallic of these four options? And looks like I don't have a poll for this. So I'll give people a couple minutes. No need to tell me what it is in chat. Just like if you have a piece of paper, write down your choices and we'll go over those in a minute or two. But the hardest part of this really is just to find the elements on the periodic table. So use this time, get yourself acquainted with the periodic table, and we will look at these. Should we categorize hydrogen in the 8A group as far as trends go? Not necessarily, because hydrogen wants to lose an electron. So it has good ionization energy. Hydrogen's just its own thing because it's just one proton. So you can't, it's hard to group it with anything, to be honest. It has trends like it's in group 1, but then it's not a metal. So it's its own creature that doesn't fit into a category, I guess. All right, so hopefully you had enough time to write down your selection. So let's take a look at these. So I'm going to go back to the periodic table because to really do this, you need to know where the elements are. So our first choice, our first contestants is we're comparing SR to SB. So SR is further to the left. So SR is more of a metal than SB. So first one is SR. The next one is BI versus AS. So AS is right here, element 33. BI is element 83. BI is further down the periodic table. So BI is more metallic than AS. Next, we're comparing AS versus S. So AS is down into the left of S. So AS is more metallic. And lastly, PB versus SB. PB is right here. SB is right here. So PB is down to the left. So PB is more metallic. Basically, like I said, whatever to the bottom and to the left of the periodic table is going to be more metallic. So just to recap, your answers there are SR, BI, AS, PB. Questions about metallic characteristics of elements or periodic trend. And that's why we go over problems like this. So make sure you get it wrong during class and hopefully not wrong during the test. All right. The last thing, yeah, we're almost done. Like I said, short class today. Last thing we're going to look at is how do you predict reactions in chemistry? And this is the question that I get all the time when I'm writing reactions up. The number one question, well, I get many questions, but one of the most frequent questions I get is, how did you know that reaction would produce that? And most of the time I answer, it's a gut feeling thing. Like, you do this enough, you know how things are going to react. Well, let's look at some guidelines to understand how elements react. Okay, so we're going to look at alkali metals, our group 1 metals, and halogens here. And we already talked about some of this at the beginning of class, or not beginning of class, beginning of the semester. And we already talked about it this week as well, talking about electron affinities, and today with ionization, talked about it talking last week with ionization energies and today with electron affinities. But your alkali metals, your group 1 metals, they really want to become +1 ions. Your halogens really want to become -1 ions. So what happens when these two react? Whenever you have a group 1 metal in a halogen, the same reaction will always happen. The alkali metal will give the electron to the halogen. You'll then have 2 ions, a positively charged ion and a negatively charged ion. You'll form an ionic bond. This is exothermic. It will produce heat energy. That's what's going on in this beaker. You have a metal plus a halogen gas. They're reacting to form a salt, and that light you're seeing is the energy from that reaction. If you were to put your hand on this beaker, it would probably feel incredibly warm because of all the energy that's being released from this reaction. And the other type of reaction we're going to look at, so question here, so sodium chloride will be exothermic, but it's neutral. So when you take solid sodium and gaseous chlorine, the sodium will donate an electron to chlorine. So you'll make sodium plus and chlorine minus. So the actual elements in there are positively charged and negatively charged. But when salt comes together, since you have one positive and one negative, overall the molecule is neutral. And since sodium really wants to lose an electron and chlorine really wants to gain that electron, overall the energy of that is negative. It's a spontaneous reaction. And if energy is negative, that means it's exothermic. That means energy is being released. One way we can feel energy is through heat. So yes, it's neutral and exothermic, but the sodium and chlorine itself are charged. So the next reaction we're going to look at is what happens when you put metal in water and group 1 metals. So like we said, group 1 metals want to become +1 ions. Water in reactions, one of the things water does is that it can split into hydrogen gas and OH- ions. Now, this doesn't always happen with water. So I'll just put that disclaimer out there, because if that always happened with water, imagine you're on a boat and you decided to have a old school cigarette and not one of these e-cigarettes. So you took out like a book of matches and you lit the match. If water always split into hydrogen gas, what would happen the moment you lit that match is that you would explode, and you would explode the whole ocean, because there would just be hydrogen gas everywhere, and hydrogen gas is super flammable. That doesn't happen, thankfully. So that was just a disclaimer in saying water doesn't always split into hydrogen gas and OH minus. But if you add a metal to it, it does. And so down here, we are adding different alkali metals. So we put lithium in water, sodium in water, potassium in water. You can see there's fire, because what's happening is that you are creating this hydrogen gas. You're forming new compounds, and the energy being released is enough to light this gas on fire. If you ever want to do a super fun experiment and you can get yourself pure sodium, which is not easy to get because it's super poisonous. So you can't just go to Walmart and buy pure sodium. But if you could buy pure sodium or pure lithium, go to a body of water and throw it in, what would happen is a giant explosion because of all the energy being released, and the hydrogen gas would light on fire. So if you're bored today and if you want to see science in action, go to YouTube and just like Google sodium in water or something like that. And you'll find some crazy chemistry professor showing that off, where they take like a brick of metal, throw it in water, and there's a giant explosion. But that's what happens when you mix an alkali metal with water. Alkali metal will become +1. Water will split into H2 gas and OH ions. So the last thing I want you to do, last thing today, is I want you to predict, based on what we just talked about, tell me what will happen when I have these different reactions. Tell me what will happen when I take strontium and iodine gas, take lithium with H2O, hydrogen gas with Br2 gas. So when doing this, you need to ask yourself, like, what happens to a metal? What happens to a non-metal during a reaction based on everything we've talked about in this semester? And do make sure it's balanced. And make sure that everything makes sense chemically. All right, so let's work through A in case you're still a little confused. We have strontium with iodine gas. So your first goal is to find these on the periodic table. So strontium, and my pen, like I said, is a little weird, so excuse my bad writing. Strontium plus I2 gas. So strontium is a group 2 metal. So a group 2 metal wants to become a +2 ion based on everything that we talked about. Iodine is a halogen. So iodine wants to become a -1 metal. And so for this to be balanced, it would be SRI2, and it would be a solid. Because iodine wants to be -1, strontium wants to be +2. So I need 2 iodine for every 1 strontium to be a neutral compound, right? It would not be correct to put SRI. That is not what it will make. It will make SRI2 every single time. And we know that by looking at the charges our atoms will make, right? If you know what charges, what ions your atoms want to make, then you'll be able to predict what compounds you're going to make. So B, we have lithium plus water. So lithium solid, don't forget your state symbols like I just did, plus water. So lithium is a group 1 metal. Group 1 metals want to become +1. Water, when mixed with metals, what will happen, like we said on the previous slide, is that we'll form hydrogen gas plus hydroxide, OH minus. So let's take a look at what that's going to be, right? So we have hydrogen gas, because we said that's one of the products, plus now lithium is going to make a +1 ion. We're going to have hydroxide make a -1 ion. So those are going to come together for lithium hydroxide, probably be aqueous because we're in water here. And now we have to balance it. So we have 3 hydrogens on the right, 2 on the left, so I need to balance that, put a 2 right there. 4 hydrogens on the left, 3 on the right, 2 oxygens on the left, 1 on the right. So I need to balance out my oxygens, then balance out my lithium. And that should be a balanced reaction. 2 lithium plus 2 water makes hydrogen gas plus 2 lithium hydroxides. Before I go on C and give you a minute to soak that in, and any questions about how I got A or B? How do I know if it will become a solid, aqueous, or stay a gas? Okay, so ionic compounds are like always solid for the most part. So anything that's a metal plus a non-metal, unless you're in water, will be solid. It for gases, hydrogen by itself is always a gas. A halogen by itself is always a gas. Basically, non-metals by themselves are going to be gases, except if you're like carbon or silicon. Your nitrogens, oxygens, fluorines, sulfur, chlorines, bromines, iodines, those are gases. So, and in your noble gases. So non-metal outside of carbon, silicon, phosphorus, aluminum, stuff like that are most likely to be gases. If you're working with water, as we were in question 2, you see we're in liquid water. Any ionic compound you make will dissolve. And so any ionic compound you make will be aqueous. So those are the rules that I'm going by. Ionic compound, not in water, solid. Ionic compound in water, aqueous. Non-metal by itself, probably a gas, some exceptions. Everything else, going to be a solid. There's only a few exceptions of a element that's liquid at room temperature. Does anyone know what is a liquid at room temperature, by the way, other than a pure element? Just your random chemistry trivia. Could you explain A again about wanting to gain and lose an electron? Sure. So strontium is a metal. Metals want to lose electrons. Iodine is a gas, or iodine is a halogen. It is a gas, but it's a halogen. Halogens want to gain electrons. Strontium's in column 2. Anything's in column 2 is going to be a +2 ion. Any halogen is going to want to form a -1 ion, because that's where they are in the periodic table. And so you'll make SRI2. Mercury, that is the correct answer. Everyone's favorite element. The poisonous mercury is one of 2 that's a liquid at room temperature. I forget the other one. Mercury is the best example. I think the other one is, yeah, I don't know. But any other questions about A and B before I get the C? Bromine is the other one. I thought it was bromine. Yeah, bromine's a liquid at room temp, apparently. Is it just for metals or just alkaline? All metals are going to become positive. The only charges we know for certain are group 1 and group 2 metals, and zinc, aluminum, and silver. Every other metal, we have no idea what the charge is going to be until the actual reaction happens, right? But group 1 and group 2 metals, group 1 metals are always +1, always, always, always. Group 2 metals are always +2. Silver is always +1. Zinc's always +2. Aluminum's always +3. Transition metals have different charges they can be. All right, let's go over C then. We have, get my pen back out. Okay, for C, there we go. We have hydrogen gas plus Br bromine gas. Okay, hydrogen is one of the weird elements, but it does want to become a +1 ion. Hydrogen always wants to be +1. Bromine is a halogen, so it always wants to be -1. So they will form a 1-to-1 ratio. You are going to be tempted to write H2Br2. I know you are. That is not correct. It is 2 molecules of HBr. The way you know that is you need to look at the charge. Hydrogen forms a +1. Bromine forms a -1. Therefore, they're always going to combine in a 1-to-1 ratio. 2 hydrogens and 2 bromines will not form together naturally under normal conditions. And let me put the state symbols. HBr, that is probably going to be a gas. Group 1 and group 2 always want to lose an electron. Yes. You will never have a reaction in normal conditions where your group 1 or group 2 don't lose electrons. I'm sure those conditions exist, but you'll need some really weird temperatures, really weird pressures, really weird chemistry for that to happen. And that is way outside the scope of general chemistry. So all group 1's always +1. All group 2's always +2. Silver +1, zinc +2, aluminum +3. All other metals, some kind of positive charge. All right. Any questions about how to predict chemical reactions happening? It's not that your brain is tiny. It's just that you're trying to pack a lot of information in. Brains can only upload so much information in a day. Well, if there are no questions at this time, that's all I have for you. So as always, if you have questions, I'm available for emails. Send me one of those. Feel free to book a meeting. I do private appearances one-on-one. Otherwise, I'll put a homework out. Have a fun, spooky Friday the 13th. When is exam 4? I think exam 4 is the 23rd or the 30th. Let me double check that. On the 23rd. Let's see. I am in the wrong class. Just pull up the syllabus. Yep, I have it down for the 23rd. That's when it will be. And we will have class after the 23rd, like in the last week of, or the first week of December. Those, I'll just say that right now. Anything we cover there, it will be on the final exam. We just won't have a test over it. So you will see final exam will have a little bit of new material, but most of it will be old material. All right. With that, have a good weekend, everybody.